Welcome back to the channel, and in today's video you're gonna go through a set of structural drawings. I have to admit that I had a lot of trouble trying to figure out how to read structural drawings when I first started working in the industry. So if you are a carpenter, apprentice, draftee, builder, young engineer, architect, and even if you don't work in the industry but you might be building your house, this video will help you to understand how correctly follow the structural engineer's instructions, which is pretty much what structural drawings are. They are a set of instructions given by the engineer, and it's essential that you get it right because that's the skeleton of your house and you don't want to get that wrong. Alright, so let's get into it. These drawings are a courtesy of ESC Structural Engineers on the Gold Coast. On our first page is the general notes. So general notes are common to any set of drawings, and the notes are usually organized to help you understand how the building is put together. So if I read here structural steel, I can expect seeing steel members in this project. If I read concrete or timber framing, that means I will see these materials throughout the project. We start from the top left corner. We've got a couple of general notes about the drawings and the contractor responsibilities. We also have the design loads that the structural engineer considered to design the house. So if you're a builder and you need to include items that are outside of the scope of work of the structural engineer, like trusses, windows, or any proprietary structure, you can pass on this information to the manufacturer and they will design this item according to these loads. Down here is the foundation notes. This item is super important because it is where you will find the soil report number, name of the company which performed the soil investigation, and the site classification. The foundation is the base of your house, and you want to make sure the footings are founded into adequate material, because once it's done, to rectify any foundation problem is extremely difficult. And it's the builder's responsibility to make reference to the soil report and its recommendations. So basically, you should go through every note on this page and make sure you understand everything you read, and if in doubt, ask your engineer. Also, on the title block, it says here issued for construction, so I expect this to be the final drawings. If it says issued for tender or preliminary, you should not be building off this set of plans. So to summarize, by going over the structural notes, what I've learned is that this building is made of a bunch of different materials like concrete, steel, and timber, as well as that the structural engineer wants me to follow the instructions and the specifications shown on this page. Moving to the next page, plans tend to go in sequence from bottom to top. So our first plan should be the footing and slab plan. When it comes to slab on ground, we have two main systems used in Australia. First one is a raft slab, and the second one, which is what we've got here, is a waffle pod slab, which is built on top of a flat ground. And this waffle pod slab consists of an edge beam that goes all around the house and a series of narrow internal beams, which is represented by these dashed lines. By the way, a dashed line means that the element is not visible in that plan. Okay, so for instance, BP1s are concrete board piers and they are under the beams. That's why we use dashed lines. Same for the grid of beams, which are located under the slab plane. What else I can see here is that under every load-bearing wall I have a larger beam, and the same applies to point loads. And how do I know what these symbols represent? So it should be all in the bottom of this page. So here this symbol denotes load point, and LBW denotes internal load-bearing wall. The slab should be 85 millimeters thick, 25 MPa concrete with a layer of top mesh. Here you have information about reinforcement and cover of beams and slab. This letter X denotes trimmer bars to all negative corners for crack control. So if we zoom in on the plans, you will find this letter X in every re-entrant corner of the slab. They will prevent cracks to appear. I can also see some of the pods have this hatch. Let's see what that is. So denotes locally reduced pad level or pod height to maintain slab thickness in set down areas. Refer typical sections and details. So let's have a look at this detail. So basically we have a step to an outdoor area, and we need to reduce the pod height to maintain slab thickness. We also have some SC1s, PF1, SF1. SC1 denotes steel column, and if you want to know the size of this column, you should refer to the framing plan. PF1 is a pad footing, and sizing reinforcement can be found on the footing schedule. SF1 is a strip footing. On the top corner there is a note saying that all footings should be founded into sandy clay with minimum 100 kPa allowable bearing capacity. So my understanding is that we will not achieve 100 kPa at ground level, and this is the reason the engineer specified board piers to support the slab. Next page should be the details for the footing and slab plans. So let's zoom in a typical waffle pod slab section. This narrow beam is called ribs, and it has 1 and 12 rebar central, represented by this circle. This was dashed line on the plans because it's underneath the slab, as you can see here. On this side we have a brick veneer wall, which consists of a brick and a timber wall separated by a gap. So if I go back to the plans, you can see these walls here. So brick on the outside and timber on the inside, and where I don't have anything, it means there is a door or window or any sort of opening. Going back to the detail, this edge beam is 300 wide by 310 deep with 3 L11 TM at the bottom. So TM is trench mesh with 3 longitudinal bars of 11 millimeters. And then we have a typical slab which is 85 millimeters thick, reinforced with SL82 mesh at the top, which is this dashed line here. Let's jump to the first floor framing plan and try to figure things out together here. Looking at this corner, we have 3 timber posts. We have a steel beam, a deck beam, deck joists, and a couple of steel columns. We do have some symbols here that I don't know what they denote, therefore I need to look for the legend, right? So we have a hashtag, this letter C, and we also have this SC1 in brackets. So looking down here, C1 denotes column post above only. Therefore I know that these 3 posts are above only. Okay, so they're sitting on the steel beam. C1 in brackets denotes column or post under only. Okay, so this SC1 is under this steel beam, therefore supporting this steel beam. Okay, easy. And then the C denotes continuous. So this column here is continuous from the ground floor to the roof. Okay, cool. And the hashtag denotes floor beam to be within the plane of the joist. Okay, so we know that the beam and the joists are in the same level. So the deck joists run in plane with the steel beam. We've got FJ3. FJ3 is 360 I joists at 450 centers, floor joists, and they run from top to bottom of the page, being supported by these walls and lintels. So FJ3 starts from here to here, and then FJ2 goes from here to here. This hatch denotes wet area set down, which could be a bathroom, for example. That's why we have a different size of joists in this section. So FJ2 is a 300 I joist, which is 60 millimeters shallower than FJ3. Therefore, it creates a 60 millimeters step to the bathroom. So note that in this section here, the engineer rotated the joist. So FJ3 runs from side to side of the page, and it's being supported by this wall here on this side, and on the other side by this nib wall, this lintel, and this beam. This B3 continues, spans from this wall, lands on this steel column under, picks up this other B3, and then lands on SB2, which is a steel beam. SB2 is supported on this side by a steel column under, while on the other side is being supported by a steel lintel. Notice that I've got hashtag, 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 and SL1 doesn't have a hashtag. So I'll quickly show you some details so you can understand this better. So B3 connects to B3. They both have the hashtag symbol, which means they are in the same plane. The steel lintel didn't have a hashtag symbol, and that means the steel beam will land on top of the steel lintel. They're not in the same plane. If they were in the same plane, the detail would look like something like this. So let's pan around a little bit. We have a set of stairs here. There's a void here, another void here. There's a wing beam next to the void to deal with the lateral forces. There's this little symbol here which denotes load point on no load bearing wall. So this beam 3 is landing on this non-load bearing wall, therefore the builder needs to provide extra studs under this point load. Okay, in this section we have some roof beams and trusses. So this tells me that the floor framing finished here, and the lower roof framing started here. Let's jump to the roof framing plan now. I'm gonna have a look at the member schedule first. So we have lintels, roof beams, trusses, hip trusses, girder trusses, and truncated girder trusses. There are no size for the trusses because they're designed and installed by a truss manufacturer. However, the engineer will still do a layout with the trusses location so we can identify the load paths and design roof beams and lintels. And there's a note on the top of the page saying beams, lintels, and tie downs design has been based on the truss layout shown. Truss layout to be confirmed by truss manufacturer prior to construction. And that's because if the truss layout changes, the load path may also change, and the structural elements may have to be reviewed and redesigned. So we've got lintels here. Lintels are beams that go inside of the wall and span openings where windows and doors are installed. So we have lintels at all openings in the external walls. Truncated girder truss are usually located 2.4 meters away from the external wall. I'm seeing that we've got a couple of roof beams. Those three timber posts starting from the first floor now are in brackets because they are under the roof framing. And the way you read this framing plan is pretty much the same way you read the floor framing plan, so I'm not going to spend much time here. So next page is the framing details. This page is going to be organized in a way that the builder can understand how the framing is put together. So for example, on the framing plan we have B3 to B3, and B3 is a 360 LVL. Therefore, if I go back to the framing details page, we should have a detail on how to connect a 360 timber beam to another 360 timber beam. So let's find another example on the framing plan. So we've got B3 is connecting to SB2. B3, as we know, is a 360 timber, and SB2 is a 300 PFC. So going back to the framing details, if I'm a builder, I know that I'll have to weld a 10mm plate to the PFC and bolt that to the timber beam with 4 M12 bolts. And that's how you read any other detail on this page. You go to the framing plan and you find the connection on the framing details page. Next is the ground floor bracing and tie down plan, which is where the structural engineer will specify the required amount and length of plywood bracings and tie down rods. So plywood bracings are sheets nailed to the stud walls to resist the wind force, and the tie down rods, as the name suggests, are steel rods that hold down the structure against wind uplift. So let's start from the notes. All external and internal load bearing walls require M12 1800 tie down. So in other words, the builder will have to identify all load bearing walls and install M12 rods spaced at 1800 millimeters. At the bottom of the page we have some forces in kilonewtons, and what this means is that the engineer calculated that for this specific house the wind loading might get as high as 71.4 kilonewtons in this direction and 56 kilonewtons in the other direction, and the sum of the capacity of all bracings is the provided force in kilonewtons, and obviously needs to be greater than the required. So if we look at the plan, we have 600 millimeters long steel truss, which could be a power truss or a net brace. I'll show you how it looks like here. So this is a power truss detail. We have roof straps, and we also have the ply bracings. So P2 1200 is a 1200 millimeters long ply bracing, and P1 600 is a 600 millimeters long ply bracing. I'll show you the difference between P1 and P2 shortly. So first floor bracing and tie down is the same thing. And then we have the bracing details page, which is where we're going to find the difference between P1 and P2. So P1 offers a 6.4 kilonewtons per meter bracing capacity, and it requires M12 rods at each end, while P2 offers a 6 kilonewtons per meter bracing capacity for a minimum 900 millimeters length. It doesn't require rods, but it requires M12 bolts at each end and at 1200 maximum, and also the spacing between nails to the top and bottom plates are reduced to 50 millimeters instead of 150. We do have these other two methods here, but they're not used much from my experience. Next page shows us how to connect these bracing walls to the floor and roof diaphragm, and also the power truss as I showed before. And finally, on the last sheet, you will find specifications on how to frame the stud walls, including size of studs, top plates, bottom plates, noggings, and also a couple of notes about the tie down, window sill or lintel trimmers. And that's pretty much how you read structural drawings. Hope this video was helpful to you. If you have any questions, just drop a comment below, and I will see you in the next video.